All right, folks, now that we looked at this animation up here and looked at gases by themselves, what I want to do is talk about microscopically, what did we see the particles doing? And then the second column is macroscopically, what would we sort of measure in the real world? And the first thing we saw was pressure. And we said the particles were basically bouncing off the walls. Particles collide with the walls of the container. And what we were seeing macroscopically, we were just measuring pressure. Like we might use a gauge. So what we're measuring macroscopically is pressure with some sort of gauge or instrument, and what that's coming from is the particles bouncing off the walls of the container. And then remember, we heated it up a little bit, and we said, well, what did the particles do? Well, temperature is sort of the speed of the particles. It's more complicated than that, but that's reasonable for us. So you go, oh, microscopically, temperature of a gas is the speed of the particles. And again, macroscopically, we just say, well, we say that's the temperature. You might measure with a thermometer or some other instrument. And lastly, we said, well, what about volume? We talk about the volume of a gas, but the volume of the particles, is effectively zero. Now, that's idealized. They're not really zero. But we say they're so small that we just call them zero. So when we talk about the volume of the gas, macroscopically, we're talking about the volume of the container that has the gas in it. All right, let's go to the next page and talk a little bit more about how we measure pressure. Of course, things are going wrong, so when I printed it, I got 8.5, but it's page 8.4 in your lecture notes. So here's one way to think about this. We can do this a lot of different ways, but imagine a cylinder, empty cylinder, and it's open at the bottom, and there's some sort of area there. And if I put some liquid here, it of course has some weight. So what we can do is say, well, its pressure equals the weight of that liquid divided by the area at the bottom. That's pressure, technically force over area. Well, you do this, with a car tire or a bike tire or something, and you say, oh, PSI. Well, what you mean there is pounds per square inch. So you've already kind of used this. Oh, weight over, PSI is pounds per square inches. Now here's another way to think about it. Imagine this. What if I took this height of this column of this H for height? What would happen to the pressure if I doubled that height? Well, I would double the pressure. So another way to measure it is we might say, well, what if I just measure the height of some column of liquid and say, oh, that's the pressure. Well, we can do that in typically, typically we use mercury. It's very heavy. And so somebody else could say, oh, we can measure this in the height of the column of mercury. Millimeters of mercury. There's many units of pressure. We're going to use 2 or 3. We can come down and look at this. This is a local station, reports 29.5 inches of mercury. So they just measured that column. Well, the rest of the world would think about it as millimeters of mercury, so I could convert that. 29.5 inches of mercury to millimeters of mercury. And you know what we're going to do? Well, I don't know. I guess I'd put inches of mercury, millimeters of mercury. that's what I would need. And in fact, there's the conversion right there. So, 25.4 millimeters of mercury for every 1 inch of mercury. And I think we get 749 millimeters of mercury. We're measuring that pressure by just specifying the height of a column of liquid. Let's look at one more thing about pressure here. This is page 8.5. Of course, it's screwed up, but it's page 8.5. So here are the sort of common pressures that we'll run into. Ag, construction, you guys will think PSI. Medical folks will mostly think millimeters of mercury. So there's our conversion factors. We don't have to have those memorized. And we could do a problem here. Let's see, I had a couple of problems made up. And I have misplaced them. No, I haven't. Let's do a couple of problems. One, let's convert tire pressure, 35 psi to atmospheres. 35 psi, typical pressure for a car tire. So I'd go 35 psi and start thinking about what conversion factor to get to ATM. Well, I'm going to want psi here, ATM here. I should have said this earlier, but the idea here is ATM came from the idea of what's the pressure of air at sea level. We said, let's call that 1 ATM. When we measured 1 ATM, we came up with about just shy of 15 psi, which is 760 millimeters of mercury. Now, the guy that was doing the experiments with all this several hundred years ago was Torricelli. So he got his name, Torricelli's or Torr's, and millimeters of mercury are the same thing. So that's the derivation of that. We don't care that much, frankly. We said, well, 1 ATM, 14.7 psi, and I get 2.4 ATM in that car tire. So there's about 2.4 times the pressure that we have in the air inside that tire. Let's do one other one for the medical folks. Let's see, I think blood pressure gets to be hypertensive if the systolic, the number on top, gets up around 140 millimeters of mercury. We might not have a sense of that. We say, well, why don't I convert that to psi? So, psi, millimeters of mercury, or torr, and I've got 14.7, 760. And if I did my math correctly, I get 2.7 psi. So a couple simple conversions. We're not going to do a lot of different units. It doesn't seem very high, but I guess that's high enough to be a problem for your patient. So we're going to go to another demo before we start page 8.7, and then we'll come back at 8.7.